Well, we're going to get going here on our curved beam topic. This is another topic that is a little bit isolated in the course. It's not necessarily strongly connected to anything else, so we're doing a few of those here before the second exam. By way of introduction, let me just sort of show an example of the type of thing that I'm talking about. And this is a very classic example. Something that's shaped like a hook, experiences bending as a result of a load like the one that I have shown. It's not showing there yet. There it is. So there's the hook that I was talking about. And whenever you load a hook like this in this way, it experiences stresses in several places. And let's just, as an example, look at what if we were to section it, kind of cut it off right here, and look at the stresses that are induced in the member at that point. What's interesting is that the curved shape of this thing that acts like a beam, and when we say beam in engineering, we're talking about a member that is carrying flexure. Okay, so that's this. We have a kind of a specific meaning of the word beam whenever we're talking about this in engineering, and this is carrying flexure at that little section right there, and it does so in such a way that it has a large, or kind of a large-ish tensile stress toward the inside, but instead of it being a linear relationship relative to the size of the beam, it actually goes to where we end up compressive on the other end, and instead of this being a linear relationship, it has a relationship that goes more like a curve. So it's kind of something more like this. Okay, and that's induced, that stress profile is induced because the beam itself is curved. It starts out curved before you ever put a load on it. Okay, one of the things that this does, there's a few interesting aspects that this brings out. One of the things that it does is that it puts a different location for where we would say the neutral axis is located relative to where the centroid of the cross-section is located. They don't end up far apart. They're usually still pretty close together, but they are not completely coincident anymore. All right, so that's one of the things that happens as a result of having a curved beam. We're used to always saying for straight beams that the neutral axis occurs on an axis that goes through the centroid of a cross-section, and whenever we talk about curved beams, that is no longer the case. Okay, and so one of the parameters that goes into the analysis of these is what they call E, which I believe stands for eccentricity. That talks about how far apart those two locations are, the location of the centroid and the location of the neutral axis. Okay, so that's one of a couple of the items that I wanted to kind of talk through is just this stress profile is nonlinear, and it creates this situation where the neutral axis is no longer located at the centroid. Okay. Another factor that I'll mention here real quick, and we're going to use it in the example problem that I'll do in just a second, is that if I was to, for instance, take a free body diagram, like cut this hook off, and I'll just do a rough idea of what that free body diagram would look like, something like this. Cut it off right there at that location. Okay. One of the things that we can't ignore about a problem like this is that there is going to be a reaction at this cross-section that reacts against the force itself. Okay. Otherwise, you wouldn't be able to have equilibrium for this body, for this portion of the body. But the other thing that has to happen there in order to react, because if those are the two forces that we have, it's not going to be in equilibrium yet unless I add something else, right? So there's going to be another reaction that has to happen here that keeps it in equilibrium. It has to have both a force reaction and a moment reaction, and that moment reaction is a bending moment. Okay? The thing I want to point out here is that we have to be careful for these problems to make sure that we identify any additional normal stress that's induced in a cross-section due to the fact that there is just that direct normal force, the direct force itself that has to be reacted on that surface. So essentially what we'll have to do is we'll have to add together a portion that is coming from flexure and another portion that's coming from basically an axial load that is being supported at that cut as well. Okay? So there's those two things. Let me also do this. I'm going to point your attention to the page in the book where a lot of this stuff goes on. It has a figure that you want to be familiar with on page 132. And then there's a few equations. The first ones I'm going to show you here are an equation for the stress on the inner fibers. So that would be this stress right here. All right? That's the stress on the inner fibers. And the equation for that is the bending moment that happens in the cross section. Okay, there's a C value. This is kind of like the C value in MC over I, and that is to the inner surface of that curve as well. And then in the denominator, we'll have a cross-sectional area. That's a little bit different. We'll also have that parameter that I mentioned a second ago, E. Make sure that you don't confuse that with the base of the natural log, right? It's not that. It's just we're using the letter E to match what they have in the book. And then R sub I, this refers to the radius, because every curve that we have, we're going to assume that we have a radius of that curve. This is the radius from the center of the thing, which I guess would be something more like right here. And it would be the radius to that inner surface from the center of the curvature. Okay, does that make sense? So this is one of the equations that we have. This is stress on the inner fibers of the beam. Okay, we also have a similar one for the stress on the outer fibers of the beam. This one is similar in form, M C sub O over A E R sub O. Okay, and the stress that we're talking about there is the stress on this backside.
How is it that both of them are like positive? Shouldn't be one of them in compressive, one of them in tensile, so it should be like a sign change.
Yeah, so actually that is something that I missed, so I'm glad that you brought that up. This one should have a minus on it, and I just left it off. Very astute. All right, and the other equation that I want to point out here is the one right above that. By the way, these are both listed here as equation 365. There's an equation right above this where it gives you a formula that gives you stress anywhere you want throughout the cross section. Okay, so that other formula is the stress is equal to my over A E R sub n minus y. Okay, and if you want to know what y is, you can look at the figure that's over on page 132, and it shows you that y is a distance that is measured relative to the neutral axis. Okay, so it works the same way as regular beams. We're measuring those values relative to the neutral axis. Okay, and this is equation 364. Okay, I want to just put these up here just so that you see that there are some equations that do some things. It gives us our stresses at the inner and outer, as well as the stress profile throughout the entire cross section. All right, and then one last thing as well. We have table 3.4. Okay, I'll mention that down here. Table 3.4 gives us some nice formulas to be able to find a couple of different things. Those two things are the radius to the centroid of the cross section and the radius to the neutral axis. Okay, so and these could be a little bit difficult for us to find if we didn't have a nice table that showed various common cross sections that we might end up with. And by having those there, it saves us the effort of having to try to derive those formulas. Okay, so these are kind of our tools that we have to work with. Let's do a problem. This problem is a little bit more design oriented, okay? The idea here is that we want to put a tow hook on the front of a vehicle, and we want this tow hook to be able to withstand 3,000 pounds of load in the middle of the hook there, just like it's shown. And what we want to do is we have two parameters that we are going to try to control to achieve a particular outcome. That outcome that we're trying to achieve is a factor of safety of 2 against yield that occurs at both the inner and outer fibers of the beam. Okay, so this is kind of interesting because there's going to be a different amount of stress expected toward the inside than toward the outside, but we can affect that somewhat by changing the geometry of the cross section. In other words, we don't have to just use a rectangle. We can change and we can maybe add more material toward the inside, for instance, of a cross section in order to support the stress where it is located. Okay, so what we're doing for this particular problem is we're taking a square tube, and that square tube has a 3/4 inch side to it. So it's 3/4 inch by 3/4 inch outside dimensions of this square tube right here. Okay, and we are going to weld to that an additional strap of material. So imagine bonding onto this square tube. We're putting an additional strap of material that has a thickness of C, and by doing this, we're hoping to put more material to the side where we're expecting the stresses to be higher. All right, so kind of trying to be smart about how we use our material and understanding how this stress distribution is going to happen. Okay, let's assume we're going to make this thing out of 1095 steel, normalized 1095 steel. So I tell you what, that's a good place where we can start. That's not that hard to get the value that we need for 1095 steel. If you look in table A21, rather than take a bunch of time with that right now, table A21 is where you find this material. And what matters to us is the yielding strength. Which we can look up as 72 KSI. All right. And what I've shown you here in terms of this picture right down below the problem, this is an entry out of table 3.4. So this is a cross section right here that we can use to model what I have proposed as the cross section of this tow hook. Okay? And how I know this is that they actually give us two different T values. We can have a different value for the T sub O than for the T sub I. All right? So how we can use that in this problem is we can take the thickness of C, which is that strap of material we're welding to the inside of the hook, and add it to the thickness of the original tube, whereas we would not have that on the back side. Okay? So this is a very useful entry for this particular shape that we are looking at. I'll just point out some of the other things that we know. We have a 1.75 inch radius. That radius is not to the complete inside of the hook. That is the radius to the interface between the strap and the 3/4 inch tube. Okay, so whatever size the strap is, it'll go to the inside of that. And then the dimension to the outside is 2.5 inches.
Where does the strap go, Dr. Swanbom?
Okay, so let me actually, it's not a bad question. Let me try to draw a quick little three-dimensional representation of this. Imagine this hook doing something like this, and maybe something along these lines. This would be the tube, something like this. This is the tube bent. And, what we want to do is add some material onto this, and so we're proposing to take a strap of material and basically add it on right here, beefing up the inside of that hook. Does that help a little bit? Okay. All right, so there's what we're trying to do. The hardest part of this whole thing is just dealing with these big nasty equations. So I'm going to go ahead and start plugging and chugging. Actually no, I'm not going to do that just yet. One of the things I want to do first before that is to analyze at this cut what kind of force and bending moment do I generate right there. That's actually the first thing I'm going to do. All right, so let's take a look at that. We have a 3,000 pound force pulling right here. And the only thing that's a little bit tricky about this is to make sure that we understand where exactly we assume that this force is applied. And the recommendation that it has in the book is that we actually use the centroid rather than the neutral axis location. Okay, so we find wherever the centroid is located of the cross section. And we apply our 3,000 pound reaction that we would have to have here. As well as a moment that happens around that point. Okay, but one of the things that we'll need to know in order to know that moment is we will need to know this length. What is that length relative to our variables? RC. Okay, so this is about as far as I can go just yet. But I did want to make mention of this right away here, is that we don't have a case where we have just a pure bending moment. We have a bending moment as well as an axial force that's happening at that cut. And it's another point that I'll make is that we're imagining this cut just to the downward side of where it starts to curve, right? If it's to the upward side before it starts to curve, well, now you're at a straight beam situation again, right? So we're looking at the case right after it begins curving so that it's a curved beam situation. All right, so now let's figure out RC and RN, and we'll come back to that. We'll come back to that free body diagram in just a second. All right, RC. The first thing we need for RC is RI, okay? Which means that we need to look very carefully at this diagram. RI is the distance from the center of curvature to the inner surface of the hook, okay? So for us, that is going to be, okay, 1.75 inches took us out to this interface. We need to subtract from that whatever thickness we have for the strap. Remember, we don't know that thickness yet. That's what we're trying to do, is solve for what we want that thickness to be. Okay, so I'm going to make this 1.75 inches minus C. Okay. To this, I'm going to add this big old fraction. The first term in that fraction is 1/2 h squared t. So let's look at what h is. Okay, h is right here. Okay, so this is h. H is going to be what? Okay, yeah, it's going to be 0.75 inches plus c. Okay, and that value is going to be squared. Then we need t. What is t? Yeah, what I'm going to do here is I'm actually going to take all this and put it over 2 like this. Okay? What's T? Okay. T, all right, is, this is a little bit tricky. Yeah, so T over 2 is A, right? Because it says here T over 2 is this thickness right here, and that is the A value that I have for my wall thickness of the tube, right? So it's going to be 2A, not just A. All right, so far so good? Go into the next term here. The next term is going to be 1/2 T sub I squared. Okay, and we're going to add this. Add 1/2 T sub I squared. What's T sub I? Okay, that's the, remember that's the inner side. So you want A plus C. Then the next thing we have here is B minus T. What's B? 3/4 of an inch. And then T was what? 2A. And then that's that 1/2 factor. All right. So that, yes, sir. This is on table 3-4. It's on page 135. Okay. All right, so the next piece that we need is T sub O. Okay, that's the outer thickness, and for us the outer thickness is this bottom side, right, which is just A. So T sub O is A. A gets multiplied by B minus T, which we just did that a second ago, 0.75 inches, minus, and T is 2A. Okay, and then this gets multiplied by H minus T sub O over 2. H again was what? 0.75 inches plus C. And then we subtract TO over 2, which is just A over 2. I see where you're going with that, but we have to be careful that the side walls are actually kind of defined differently than that back wall or outer wall. Okay, so there's all that stuff. Now in the denominator, H, 0.75 inches. What's T? Again, that's 2A, right? Now we have B minus T. B, again, is 0.75 inches. Yes, thank you very much. We don't want to forget that. Appreciate that. All right, 0.75 inches plus C. And then here we have B minus T. B does not have the plus C, right? We subtract T. T is 2A. And then we multiply this by the thickness of the inner. Thickness of the inner is going to be equal to A plus C. And the thickness of the outer is going to be just A. All right. Good so far? You don't know, but at least you copied it all down, right? So, all right. So let's go on and figure out the radius from the center of curvature. Now, instead of finding the radius, that's RC was radius of, to the centroid, this time we're going to take the radius to the neutral axis. Okay, and that's labeled R sub n. Okay, and R sub n is given with a big old fraction again. In the numerator of the big old fraction is B. B is again 0.75 inches. Whoops. And then that's taken, that is B minus T. T is what? 2A. This is going to be multiplied by TO. I think we just did that one, right? TI is A plus C, and TO is just A. And then we're going to add to this H times T. H is 0.75 inches plus C, and T is 2A. And now the denominator. B is 0.75 inches. This is multiplied by, in the parentheses here, we have the natural log of Ri plus Ti. Okay. Ri is 1.75 inches minus C. And Ti is A plus C. This all gets divided by Ri, and Ri is 1.75 inches minus C. To this, we're going to add another natural log of, in this case, we have the outer radius, the radius to the outer fibers of the beam. And that is simply going to be 2.5 inches. That'll be divided by 2.5 inches minus, and T sub O is just A. And onto this we are going to add T, which is 2A, times the natural log of RO minus TO. And that TO is just A, over RI plus TI. Okay, RI is 1.75 inches minus C plus TI. TI is, let's see, C plus A, yeah, A plus C. All right, so what? So now we have two equations. How many unknowns do we have in our two equations? 4. Okay, we have two equations right now in 4 unknowns. Okay, the issue here is that we don't know RC, Rn, and we're looking to try to find A and C as well, because these are design parameters that we're trying to use to set the stress level at both the inner and the outer fibers of the curved beam to be at a particular level, and that level is set with the material strength and a factor of safety of 2. All right, so that's where we get our other 2 equations that we need. We actually go back up here and remember that we have equations for stress at the inner and outer fibers of a curved beam. Okay, and we're going to use these and figure out, you know, or kind of use the piece of information that we need to use about material strength and factor of safety to be able to get another couple of equations. If you look at this, E is just the difference between the centroidal radius and the neutral axis radius. So that's something that we can express in terms of these values down here. A is just a cross-sectional area, which is also something we can express. R sub I we've been expressing in terms of C and A, right? C sub I and C sub O are also values that we can find. So in other words, we can use these 2 equations without adding any more variables, and we end up with a system of 4 equations and 4 unknowns that we can solve. All right? Tell you what, I'm going to grab these, copy them, and we'll do these down here. Actually, I'll put them right here. All right. Stress at the inner fibers. Okay, that's going to be a tensile stress, right? So I'm going to take this and say this will be the strength, 72 KSI, and to get an allowable stress, right, I take the strength and I divide by the factor of safety. And I'm setting this stress level equal to M. Okay, what's M in terms of the things that we know? 3,000 pounds times R sub C, right? Okay. For C sub I, let's make sure we aren't misunderstanding C sub I. It actually has these listed on that figure on page 132, figure 334. C sub I is the distance from the neutral axis to the inner fibers of the beam. So what would that be? Okay, well, we don't know where the neutral axis is yet, right? So we want to put that in terms of R sub n, right? So we have R sub n minus what? R sub I. But R sub I we can express in terms of a couple of other values, right? 1.7 minus C. All right. Now what about the denominator? Okay, well, let's do it this way. We have, there's a bunch of different ways that we could split this up, but we need to figure out the area, right? So one of the things we can do is just sort of add the strap, which is 0.75 inches times C, okay, plus the outer dimensions of this thing are just 0.75 inches. So I'll take that and square it and subtract from that what? Yep, 0.75 inches minus 2a squared. Okay, and that's the value of the area. What about E? Okay, this one's actually fairly easy to express because we just do it in terms of RC and RN. RC minus RN. right? That's because that's how it's defined to be. The eccentricity there is just the difference between those two radius values. Okay, and then lastly we have r sub I, and we've been dealing with that one already. What is it? 1.75 inches minus c. Okay, so what we just wrote down up here, this is just for flexural. What else do we need? Okay, go back to here and we said there's also an axial force of 3,000 pounds that we need to deal with. So we need to add on another certain amount of stress. And that's going to be based on 3,000 pounds of force divided by what? The area. And the area is what we just wrote up here. It is 0.75 inches times c plus 0.75 inches squared minus 0.75 inches minus 2a squared. We're almost there. Okay. What's next? Okay, the stress on the outer fibers. And the presumption there is that that's going to be in compression, right? Although it doesn't necessarily have to be. Why not? Our presumption here is that flexural stress is going to exceed normal stress. And it usually does, in many of our cases anyway. But it is possible that we could end up with a larger just axial stress happening here than the flexural component. Okay, imagine if the length basis wasn't very large, right? The moment arm wasn't very large. You could end up with a larger amount of stress due to your axial component than you do due to the flexural component. But anyway, let's presume here that it is in compression, in which case we want to take our strength value, and because this is a ductile material, it's a ductile steel, we presume that it is going to have the same strength properties in tension and compression. So I'm going to put in here negative 72 KSI over 2. And this is going to be equal to, we're using our expression up here, negative 3,000 pounds times C sub O is how big? Actually, excuse me, I'm not ready to do C sub O just yet. What do I need to do before C sub O? Yeah, I need to figure out my, or put in my RC value. Okay, now I can do C sub O. And C sub O is what? Okay, C sub O should be the outer radius minus the radius to the neutral axis. All right, and then this all gets divided by I'll write out this area term again, 0.75 inches times C plus 0.75 inches squared minus 0.75 inches minus 2a, all of that squared. This is all my area term. E is not different than it was the last time, so it's just going to be RC minus Rn. And then RO is just 2.5 inches. the axial component distributes across the entire face. Okay, so what do I need to do there? Okay, I need this again. Whew. Four equations, four unknowns. Let's do this thing. Yeah, this would not be fun to try to do with a calculator. That's usually at this point the question that is brewing everyone's mind is, holy moly, on a test, what are we supposed to do? On a test, I probably won't give you a problem that's exactly of this style. I'm familiar with the computational tools that you have at your disposal, and I generally try to keep your tasks to within those, the level of those tools. So, all right, here it is. Okay, what we do at the very beginning is we define some things, and one of the things that you will notice is that I pick some fairly close initial guesses. Okay, this is important in this kind of a problem. Why do you think that is? So the way that MathCAD works is it's kind of a sophisticated guess and check. Okay. Some of you are kind of familiar with a Newton's method type of a way of doing some of these things. It requires an initial guess. It kind of verifies how good that guess was, makes a better guess, and keeps on moving closer and closer to an actual solution. When you have very nonlinear equations, which these are, then it kind of matters what you use as your initial guesses. Okay, so I had to be a little bit judicious about how I made these initial guesses for all four of my values. Looks like I changed my F here. Let's see here. All right, now we're at 3,000 pounds. And we scroll to the bottom. What do we see? So we want a 38 thousandths wall thickness and a half-inch strap, half-inch thick strap. Maybe, okay. I want to kind of talk through this a little bit. This problem doesn't actually necessarily make sense. Okay, I would say this problem is one that makes sense to at least try, all right, in terms of a design technique, but it doesn't necessarily make sense. All right, the reason it doesn't necessarily make sense is that you may not want to constrain both ends to be at the same stress level. All right, that may not actually be a goal that you care about. If you were actually doing a design on this, what's your ultimate goal, do you think? If you got to control those two parameters, what's your ultimate goal? Probably, at least for most designers, unless, you know, of course, a lot of things can be part of your rationale as you're designing things, but one of the main things that we design for frequently is weight. Okay, you try to minimize material. So you might look at this thing and say, I'm trying to minimize the area of my cross-section because that's how I minimize weight. Okay, and I would say that that's a reasonable thing that we could do instead. I think this is why I had that value a little bit lower up here. It's possible that by changing this value, maybe it would start to make sense to use this as a guessing technique for what these values should be. These values will make a lot better sense if we're having to support a 1500 400-pound load instead of a 3,000-pound load. What I wanted to just kind of talk through that is that, you know, sometimes we come up in our minds with a way to do a design task, and we think, okay, that really sounds good, that we'll try to equalize stress to the inner and outer fibers of this thing, and you know, change the cross section really smart, in a really smart way to make that happen, and then maybe it doesn't work out. Okay, so that was kind of my main thing that I wanted to do today. Any questions? Yes, sir.
What is the second term in each of those stress equations?
The second term in each stress equation. Okay. So I'm assuming you mean the second term being this.
No, I mean after the addition, 3,000 over times this.
Oh, this thing right here.
Yes.
Okay. Both this and this are based on the fact that we do not have just a pure bending moment. That's not the only load that this cross-section has to carry. Okay, it goes down to the drawing that I did down here. We have to carry a bending moment, yes, but we also have to carry this axial force of 3,000 pounds. It's a kind of a direct axial force that happens on that face. And so what we're doing there is just, I'll put in here direct axial stress. And that's just based on F over A. Okay, you look at the amount of force it has to carry, divide by the area over which it carries it, and you can just add that right on. As a matter of fact, it has this, I believe, somewhere in here. Yeah, actually at the bottom of page 133, it's in an example problem, okay, that they have in the textbook. And they're doing a very similar type of thing where they're adding force onto a hook. And you'll see there it's an equation labeled 2. Okay? And what they're doing is they're adding just a direct F over A amount of stress, which is a direct axial stress, to an amount of flexural stress, which is what you find using equations like 364 or 365. Good question. All right, anything else? Who wants to have a short class day today? That's a lot of hands. Okay, then we'll have a short class day. You had another question? This one right here? Okay, the reason that this one's positive is that regardless if you're looking to the inside or the outside, that axial stress component is always going to be tensile. Okay? We have this other component here that is negative 3,000, right? That's going to be a compressive stress. So you're going to have a compressive component that's happening from the flexural stress. Okay? And then the direction of your direct axial stress is going to be tensile. So they have to have different signs here. Yes?
Also, if the force is at angle, then
If the force is at an angle,
yeah, then what would the other component of force cause? Like,
okay, so if you had a force at an angle and it ended up creating a component, I believe what you're saying is it would create a component of stress that it would have to react. So I guess maybe add another force on this way. Is that what you're saying?
yeah.
That means that you'd create a component of stress that would have to act on this surface reacting against that one, right? That would be the same type of thing as whenever you did shear and bending moment diagrams. That would be the shear, right? And so, you can have that, but it's not added in exactly the same way. And the truth is, it's not going to have an appreciable effect out at the outer fibers of the beam. And because the type of stress that might create would be like a VQ over IT, a transverse shear type of a situation. Transverse shear doesn't create stress at the outer fibers, it creates stress more to the inside. Another good question. Appreciate it. All right. Well, let's call it a day. I'll see you all on Wednesday.